Guys, I'm going to be starting, so you need to have your notes out, ready to go. Reminder that the quiz is due tonight. If you have not finished it, you have until midnight. Okay, Evan, is your power back on?
Yeah, I came out once, yeah.
Oh, good. The little things in life that make
Yes.
us so much happier. So don't forget about the quiz, guys. It is an actual quiz grade. It goes in like a quiz. Okay. I'm going to do a quick homework check tomorrow, probably just one assignment. Just know that I never, when I check homework, I never check the night before. That will not be in the running as one that I choose. So like today's homework is not something I would check tomorrow. Okay, so just understand that. I'm already recording. Okay. All right, so just as a reminder, we're working on these rational functions still, but good news, bad news, whatever, however you feel about it. Today's the last day we're working on it, and then we move on to something else tomorrow. And today there's actually no new material. Everything we're doing in this is a review. I mean, going back weeks review, okay? Horizontal asymptotes, all kinds of stuff. So, and I'm going to go a little faster through the factoring and stuff like that. You know, it is very important that you know how to factor. That was the, if you remember, maybe you picked up on it, it's the absolutely only skill I reviewed from previous years, okay? I did that was the first thing we did in this class was I retaught how to factor, worked on it, had a quiz, had a retake quiz, because it's something that comes up constantly, okay? So if you are still struggling with factoring, you need to find some tutoring, okay? You've got to find some support on that because you can't get through this class without being able to factor. Also, keep in mind that if you're absent, if you're tired and you're missing what I'm saying, it looks like you're writing and you're not paying attention, whatever, you know, if you not understand or something, please use Canvas, use my videos. They will help you stay up to date and keep you on track, okay? So you can use them for review, if you're absent, whatever. But I make them every day for you, okay? All right. So let's get started. What was I going to say? Okay, so we're talking about polynomial and rational functions today. And so we're starting off with a polynomial. You should recognize this as not being a rational function that we've been working with in a last few days, or weeks, I should say, because it doesn't have a fraction in it. It's a plain old boring polynomial. And what it's asking us to do is to write an equivalent representation. That just means write it another way. And that means factor, okay? So we're going to factor it, and then we're going to sketch a graph of this polynomial, okay? So, and again, this is review. There's nothing I'm going to teach you today that you haven't learned already, whether you remember it or not. There's no new material today, okay? So remember, the first step of all factoring is to factor out a GCF. So that's what I'm going to do first. Raja, make sure you're taking notes. I don't want you working on the quiz while I'm teaching. And then this is a chart problem. Guys, I'm not writing the chart anymore. I think I've told you I don't make a chart every time I do this, or ever. I just do it as a method to teach. So I'm not making the chart. If you need to or want to, go right ahead. As I've always said, I'll never take points off for showing more work, okay? So you show more work than I do, that's never wrong, okay? But what I model for you is fine. So if I'm not showing like the chart off to the side, then you don't have to, and I'm not going to. So I'm asking myself, what numbers multiply to get negative 15, add to get negative 2? Yeah, and sometimes, you know, some people, like, who was that? Okay, Zach, I've noticed, Zach, you're very good at factoring, comes up with these numbers very quickly with the signs and everything. Just a side note, if you're having trouble, like, doing all of that in your head, but you know the numbers, 5 and 3, we're going to make a 15, and I know I can make a 2 out of that. Write the numbers down and then play with the signs, okay? But yes, negative 5, positive 3. Zach, does it matter who gets the negative and who gets the positive? Yes, it does matter. Zach, does it matter what order I write the parentheses in? No, it does not matter, okay? All right, so this is called factored form, okay? That is an equivalent form. This is standard form. This is factored form, okay? They are equivalent. To graph, we need the x-intercepts, the zeros. If we set each of these equal to 0 and solve, we'll get 0, 5, negative 3. Okay, so nothing really earth-shattering there, hopefully. Let's bring back some other little things, like multiplicity. There's only one of each of these. So in all three of these situations, they're going to cross the x-axis. Okay, remember, odd multiplicity, we cross. Even multiplicity, which we'll see in our first homework problem, we bounce. So I'll review that there. Okay, the other thing we need to talk about is end behavior. What directions are my ends going in, my arrows? And if you remember with a polynomial, we always look at the very first term. So I'm looking at the x to the third. Whenever your degree is odd, we know the end behaviors go in opposite directions. And we compare it to a line. If this was x to the first with a positive slope in front, it would go like this, right? It would rise left to right. So our end behavior is going to do the same thing. It's going to start down and up, okay? Let's just sketch this nice and easy. -3, we're going to have an x-intercept. 0, we're going to have an x-intercept. And 5. So there's my zeros. I'm going to start down and cross at each of these. The only thing we don't have is the turning point. So you turn your graph wherever you want. So you start down and cross through the -3. Go up and turn around wherever it makes you happy. Come back and hit the 0 and cross again. Turn around wherever you want. I want to cross around down here. And then cross again. And as you can see, I'm starting down, ending up. What happens in between those two endpoints is different from a line to what this is, a cubic. But what end behavior does is just shows what the ends are doing. What happens in between is different from poly to poly. Okay? So that was a review. All right, let's look at the second example. Write an equation of f of x in factored form. So yesterday we called it simplified form. Same idea as factored form. Factor it and simplify it. That's simplified form or factored form. Okay, so you might hear factored form or simplified form, either one. All right, so I'm going to factor this guy. I'm going to do it down here. I have the difference of two squares in my numerator. That's x plus 4, x minus 4. Raja, you writing? And then in my denominator, I have another chart problem. The numbers that multiply to get 28 and 3 would be 7, and add to get 3 would be 7 and 4. Who's going to be negative? The 4. And guys, just like any fraction, this is a fraction. It's a fraction. We always simplify our fractions, okay? So just understand, look ahead, we're going to have to answer a whole and a vertical asymptote. Remember, we get those from our denominator before we cancel. So if you want to write this, you don't have to. Just know we're going to be putting these two numbers over here somehow. The point I'm making here is that you don't want to make that decision with your factored form. Like if you said, oh wait, what's the whole and what's the vertical asymptote, and you just looked at what's blue, you might go, oh, we just have a VA, because there's nothing to cancel, right? But you have to look at it before you simplified. X can't be -7 or 4, but this is the simplified or factored form, okay? And again, you might notice I keep writing this off to the side, little in the margin. My point is, I don't need you to write that. You need to know that, though. You need to be able to look at your denominator and know x can't be this and or this, and or this or this, and what job they have on a graph. So as you all remember, I'm sure, because we did it ad nauseum yesterday, we will have a whole if we cancel, and we're going to go ahead and just find the ordered pair, and a vertical asymptote if we don't cancel. And remember, the way we find the y value of a whole is we plug the x in. Does it matter where I plug it in? Yeah. And I'm going to be obnoxious. It's got to get plugged into the simplified form. You'll know, if you do all this work, if you take this 4 and plug it into the original function, you're going to get 0 over 0. So you're going to know something's wrong, okay? So I'm just going to plug it in here. Again, this show as much or as little work as you want or need to. And don't forget, we always write our fractions in simplified form, or you could have written this as a decimal. So Again, to simplify a fraction on these calculators, if you didn't know how to simplify it by hand, you just divide it. Remember, you always get a decimal, and then if you hit math, enter, enter, it'll give you the simplified version of that fraction if there is one. But 8/11ths can't be simplified. That's why we don't see anything other than 8/11ths. Could you have written it as a decimal? Yep. Doesn't matter. Yep. Mm-hmm. Yep. Yeah. Let's talk about that real quick. If you were going to ever use a decimal in this class, if you're ever going to, outside of money, we're going to round to 3 places because that's it. I just want to get you guys in the habit. I mean, technically, it doesn't matter for a problem like this. Like, if this was any other class, I'd say, yeah, let's just go to, you could put 0.72 repeating or 0.73 rounding it. But on the AP exam, you are required to round everything to 3 places. So I like to just get you in the habit of that from day one. Okay, except money, of course, which just goes out 2 places. Good, Zach? Okay, let's look at example 3. Here we have r of x. We're going to write it, we're going to factor it. Write it in simplified form, factored form. Okay, so I take a quick look at that problem, and we're going to have a chart on top and a chart on the bottom. So I'm just getting set up. So the 2 numbers that multiply to get 12 and add to get 7, 4 and 3, both positive. Plus 3 and negative 2, yes, thank you, Remy, would give us negative 6 and positive 1, right? But don't forget, looking ahead, I can see I'm going to have to answer some questions about it. This is optional to write this as long as you know it. That's all that matters. X can't be negative 3 or 2, but we do need to simplify this fraction. Okay, so if this was a FRQ or, a multiple choice question, you would want to make sure you simplify your fraction. So we would write it without the x plus 3 on top and bottom. Okay? Zeros come from our what? Fill in the blank. Numerator. Remember what comes from the denominator, the a's and wholes. Okay? Numerator is where we get our zeros. Zeros are x-intercepts, solutions, all those things. Okay? Think about the one we did up here, this polynomial. Those are zeros. They all came from the numerator. You could have technically made that a fraction, right? Over 1. All the zeros come from the numerator. Okay? So if you set your numerator equal to 0 and solve it, you would get x equals negative 4. You could write it as an ordered pair. Just know this. We have seen some rational functions that have multiplicity in the top and bottom where, you might have had negative 4 canceled in the denominator, so it would have been assigned as a whole. You couldn't write it as a 0 and a whole. Every number on a graph only gets one job. You can't make them work harder than they're already working. You're either a vertical asymptote or a whole or an x-intercept. You can't be more than one of those things. How do you know who wins? Think back to that Hulk picture, okay? Vertical asymptote beats everybody, all right? So we have that. Do we have a whole? Yeah, at negative 3 something, right? Remember, if you cancel, you're a whole. So my negative 3 is getting assigned that job. And we can just easily go plug negative 3 into our simplified version, negative 1/5, or write it as a decimal if you want to. It doesn't matter. I put it in my calculator and I've got that. So you could have written either way. Bless you. Okay, vertical asymptotes again come from our denominator. So we assigned that to his job. Horizontal asymptote, we look at the degree of our numerator and the degree of our denominator. And when they are the same, we then look at the leading coefficients. So that would be y equals 1. If you write just 2 or just 1 for your asymptotes, that would be wrong. You have to put the x equals and or the y equals because it's a line. So you have to show that it's a line. If you just put the number, I would mark it wrong, okay? What I model for you here is what you should be doing. All right, you've never seen me just write 2 or just write 1. All right, and then find the domain in Sketch. Remember, I like to find my domain once I have the picture, so I'm going to sketch first, then go back and do the domain. Okay, so I'm just going to put all of these components on the graph. I have an x-intercept at -4, 0. That's a closed-in circle. That's part of the graph. It is included in the graph. Okay. Now the whole is -3, -0.2. That is a really teeny tiny number between 0 and -1. How do you graph it? Just estimate. To the left 3, down a tiny bit. Okay? Good enough. Remember, these graphs are not perfect. Vertical asymptote at x equals 2. Horizontal asymptote at y equals 1. It's a hole, so it has to be open. Okay, and that's fine. Remember what I told you guys yesterday. If you made it a closed circle, it's no big deal. I'll show you after I make this branch how to fix that. But what we learned yesterday is now we know that we have enough information to know we're going to have a branch in this quadrant, this little corner here. And then if you accidentally did this, which I do all the time, I know you guys are shocked by that, you could just show me that there would be a 0 by going like that. Okay, that's good enough. Remember, these graphs do not have to be perfect. And as I told you, these graphs can get really, really complicated. But for what we need to know in this class, it's really about knowing all this stuff and how it relates to the graph. It's not about making a perfect graph like we did in Algebra 2. So as I said to you, the only ones we'll be expected to be able to graph are if you have one of your little branches, you know the other one is going to be in the opposite diagonal quadrant. Is it perfect? No. Do we care? No, not at all. But if this was stressing you out and you really wanted a perfect graph, you could make an XY chart and pick values on either side of this vertical asymptote, plug and chug and graph them. You could put this simplified version in your graphing calculator, go to the table and pull some points off, but that's not required by me, okay? This is good enough. All right, now let's do the domain. Remember what affects the domain. Listen, what affects the domain is anything that's not included in the graph, any x values. So that would be the x value of your whole, right? That's an open circle. It's not included. So that -3 x value is not in the domain. And that vertical asymptote at x equals 2, that is also not included. We have to jump over them, okay? So we're going to go from -infinity, that's this arrow, and the first x value we come to that causes a problem is what? What? 3. Yeah, sorry, I just didn't hear you. Good job. Let's jump over it, okay? So we got as close as we could to -3, but we are not including it, hence the parentheses. We jump over it and we keep on going. Now, even though this graph is pointing down, it goes down forever. That is 100% true. But it's getting as close as it can to 2, right? Until it can't get any closer. So we're going to get as close as we can to 2, but we're not going to include 2. So let's jump over the 2, and we catch back up with our graph. It ends up here. Because remember, this graph coming from way up at the top is as close as you can get to 2 as possible, and then it moves away from 2 towards positive infinity. So remember, doing that little union thing is like jumping over them, okay? Are we starting to get the domain thing better? Did someone say no? What? Did you say no, sweetie? Okay, I'll come sit with you after we get done. Right. Yesterday, we had a problem similar to this where we had to create an equation, a function, a rational function, given some limit statements. This is similar. We're going to pull some information off the graph and create a function. And it's going to be a rough function. Haley picked up yesterday. I was impressed on that. It wasn't perfect. There were some things we could have tweaked to make our function match those asymptotes a little bit better. We're just getting some general information off this and creating a function. So let's just look at this graph for a second and pull off anything we see, and then we'll see what we can do with it in a second. So in any order, start pulling things off the graph. Like I see a VA at x equals 2. What? A hole, great, yes, we have a hole at x equals 4 right here. I don't know if I need the y value. I happen to know that the y value is a fraction. I'll just tell you that ahead of time. The y value isn't going to really matter for us for this. I see an HA at y equals 1. And there's one more important piece of information that I could pull off this graph that would make, that I need. Anybody know before I try to give it away? Who said that? Yeah, the 0, the x-intercept. Because remember, what's in our denominator? VAs and holes. What's in our numerator? X-intercepts. So if there's an x-intercept, which there is, we need it. We couldn't get that information yesterday. With the limit statements, it didn't give us that. That's why our function was kind of as perfect as we could make it. Okay, so and that's everything I really need to talk about. So we're going to create a function. The name of the function is f of x. It's a rational function, so it's going to be a fraction. And doesn't matter what order, let's just start with the x equals 2. Vertical asymptotes come from the denominator. Before it was x equals 2, it was x minus 2. We set it equal to 0 and solved it, and we got that. What we know about vertical asymptotes is it's left over in the denominator. There might have been some canceling, but there had to be one left in the denominator. I'm making this, again, as simple as possible, so I'm just going to do that. But I could put 9 of them on top and 10 of them on the bottom, right? Because 9 would cancel and I'd have 1 left. But I'm not going to get too crazy with that. Just understand there's many, many, many ways you could write this that would give you a vertical asymptote of x equals 2. Okay? The whole also comes from the denominator. And we know we get a whole by canceling with an identical factor in the numerator. Could I put 10 on top and 10 on the bottom? Sure. Could I put 25 on top and 20 on the bottom? Yep, they would cancel. Again, just giving the most simplistic version of it. The horizontal asymptote, I wrote it because I wanted to talk about that. That's something we see, but I'm not worried about it here. We'll talk about horizontal asymptotes more in a minute. But the x-intercept does come from the numerator, so that would have been x plus 3. Okay? And remember, the direction said to write it in factored form. This is factored form, but it is a fraction. You always simplify your fractions. So the final answer would be this. Oops, I don't know why I put the parentheses. They're not necessary, but they're not wrong. Okay, so you don't have to put the parentheses, or you could. Okay. Now the last bit of this lesson is going back over HAs and SAs. Okay? Complete review of stuff we did a little over 2 weeks ago. Okay? Let me just wait to see you guys writing. Next page. We're going to the next page. Are you with me, Evan? Okay. So I want to remind you, we're going to review polynomial long division in preparation for slant asymptotes, okay? So when I first introduced this a couple weeks ago, we talked about like 4th grade division. I'm not going to do one because really it's good to know how to do that. You'd see it on the PERT. Without a calculator, you'd have to know how to do that. But for this class, you would do something like that in a calculator, but we can't do this in a calculator. We have to be able to do long division, okay? So let's remind ourselves how to do it. We get ourselves set up. And even though, I mean, no one's like, yes, I love long division, let's do more. I'm hoping, you know, I like to use this terminology. I hope it's just annoying but not difficult, right? And that we get a little faster with it by the time we do a couple of these. So I'll show you some places you can make some shortcuts if you want to. the way we start is always the hardest part for people. Like, what do I do? What do I do? You always look at the first two terms. That's it. Closed your mind off to everything else. And you ask yourself, what times 2x gives me 6x squared? What times 2x will give me 6x squared? 3x. And where you place it matters. Put it with his family member, his friend, his like term, whatever. That's going to be really important in the next one we do. And then what we're doing here is the distributive property. You don't have to go off to the side and do it, but some people have like some spatial stuff. It's hard for them to see that's what we're doing here. If you like to go off to the side and distribute, do it. I'm just not going to do it, okay? I'm going to do 3x times 2x is 6x squared, and 3x times 1 is positive 3x. Remember, then we do the subtraction step, which is change both signs. And bring down the next one. And we start over again. Again, this is where students get lost traditionally. Always this 2x, but remember how we started here and here? It's 2x and this guy now. What times 2x gives you 4x? 2. Positive 2, so I'm going to put plus 2. Again, if you want to go off to the side and do this math and then insert it back in, no shame in your game. Do it. So 2 times 2x is 4x. 2 times 1 is 2. Change both signs. And we get a remainder of 3. Okay, so I just wanted to remind you that now we're going to talk about why we're using it. One thing I want you guys to notice is all of my like terms are lined up. If I did it right, that should be happening. Okay, notice only the x squareds here, only the x to the first power here, only constants here. That is important, okay? Why? Well, you're going to see on this problem. We have to write, look at this crazy looking thing. We're going to write it in factored form and answer these questions, okay? So the first step I can see in that numerator is, and I'm just going to do it right away, is factoring out a GCF. Notice how they all have an x. I'm going to go ahead and factor that x out. I'm not going to bother writing the denominator again. So I'm going to have an x and 2 parentheses, and then 2 parentheses here, because this is a chart. I'll just write it. X squared plus 8x is 15. So what I have in the parentheses on the numerator and the whole denominator are my chart problems. So I'm asking myself what two numbers multiply to get negative 10, add to get 3. I know my numbers are 5 and 2, right? Who's going to be negative? And we love it when it's all positive, right? The two numbers that multiply to get 15, add to get 8 are 5 and 3, right? Now, I am going to simplify my fraction, but this is the moment, if it helps you, you might want to say what x can't be, negative 5 and negative 3. It's up to you, okay? If you feel like you need to write that. Final factored answer, though, would be x minus 2 over x plus 3. So there's my factored, simplified factored answer, right? Now let's answer some questions. Vertical asymptote. Yep, there's something left in the denominator. It didn't ask for a whole, so I don't need to worry about that. Horizontal asymptote. And this is kind of out of order because our very last example is a very quick review of all the different possibilities, but here it is, so we'll just talk about it. Remember, horizontal asymptotes, we look at the degree of the numerator and the degree of the denominator. In this case, 3 is greater than 2. 3 is greater than 2. And you could have, by the way, looked at either one of these. This would have been 2 is greater than 1, right, if you distribute. Either way, it doesn't matter. because you would have 2 is greater than 1. So in either situation, the numerator is greater than the denominator. Anytime that happens, you would have none. No horizontal asymptote. Then you have to ask yourself, but will I have a slant asymptote? Because that's the only time you could have a slant asymptote is when you don't have a horizontal asymptote. But you don't always have a slant asymptote just because there's no horizontal asymptote. How do we know? Is this very, very simple. If the numerator's degree is only 1 more than the denominator. In other words, the difference is 1. Okay? So if you subtract these, you get a 1. Subtract these, you get a 1. If the numerator's degree is 100 and the denominator's degree is 99, yes, you would have a slant asymptote. Okay? So how do we find the slant asymptote? We do this. Okay? Now you can do it with this. That would take a really long time. So nope, not going to do that. I'm going to use my simplified version. And pretend I hadn't written that. We wouldn't use the numerator looking like that. Think about doing, I'm going to use the space up here, by the way, because I ran out of room. So you write it wherever you want. I have the x plus 3 on the outside. I wouldn't write x parentheses x minus 2. I would write it this way. Distribute it real quick. So I would have x squared minus 2x. What I want you guys to notice is that we're missing the constant. There's no number after the x, like there was a 5 here. You have to remember to put a placeholder. And that's going to come up in our very last problem in a minute, and I'll remind you of it, and I'll tell you in both situations how you would know you didn't do it, okay? All right, so again, start here and here. Ask yourself what times x gives you x squared. That would just be x. Notice where I'm placing. Distribute. X times x is x squared. X times 3 is 3x. Change both signs. Common mistake is only doing the first one. Bring down the 0. What times x gives you negative 5x? Negative 5. And technically you could really stop here because there's nothing left to bring down. We technically have a remainder of negative 15, but if you remember when I taught this to you before, we don't care about the remainder for slant asymptote, okay? All we have to care about is the x minus 5. Our slant asymptote would be y equals x minus 5. It should always be a line, x to the first power. It always will be. And we leave the remainder off. We just throw it away. Okay? We're going to do another one of those here in a second. Okay? So our last example is just a quick review of how to tell all the different HAs. Example 7. Again, horizontal asymptotes. Did I do that too fast? I feel like I went too fast. Horizontal asymptotes are found by looking at the degree of the numerator and the degree of the denominator. Remember, degree is the biggest exponent. Won't always be first, right? It's the biggest one. That's what we have to look at. So looking at our example A, the numerator's degree is 1 and the denominator's degree is 2, right? 1 is less than 2. The horizontal asymptote will be y equals 0. It's memorization. This is the hardest one to remember, so I don't memorize this one. I just know the other two by heart, and I'll explain how that as I go. So I just remember, oh, this isn't one of the ones I know, so it must be that one I don't know. So I'm just sharing with you because I'm very bad at memorizing things. I always like to give you my ways. So it doesn't matter what the difference of these numbers are. If the bottom number is 100 and the top number is 101 or 1,001, 1,000, whatever, it's going to be y equals 0. Okay? Next one, we see this one a lot. We had a ton, I think, yesterday. When they are the same, you do the leading coefficients. Okay? So it would be y equals 5 halves. So always reduce it though. If 5 halves could be reduced, you would need to reduce it, okay? Kirk? Okay. Here we have 2 over 1, so 2 is greater than 1. This is the one I always remember as could have a slant asymptote. The difference is 1. I know it doesn't have an HA, but does it have a SA? The answer is yes, it does. Why? Because the difference in these two numbers is 1. 2 minus 1 is 1. So yes, we will have a slant asymptote. That's when you have to do long division. One more here. I only put 1 in your homework. But I really wanted to do this one because it's missing the linear term. This is the quadratic term, the x squared. It's missing the x to the first, known as the linear term, but it has a constant. If you don't put that in there, you will know very quickly if you've been following my steps as I do this, and I'll show you what I mean right here. To start this, we ask ourselves, what times 2x gives us 4x squared? 2x. Remember, you always want to place your first number in the right place to get everything lined up. If you had forgotten to put the 0x in there, you would have been like, wait, where do I put it? You wouldn't have had an x column to start. So hopefully you would pick up on that and be like, oh, that's right, I forgot my placeholder of 0x. Okay, distribute. Change both signs. Bring down the -8 and start over. Always that 2x, but new guy here. What times 2x gives me -2x? -1. Yep. -1 times 2x is -2x. -1 times 1 is -1. And you could technically stop here because we don't care about the remainder. Our slant asymptote would be y equals 2x minus 1. Let me just ask you guys this one more time. Can I have no HA and no SA? Yes, you can. If my numerator was 5 and my denominator was 1, you would have none and none. Why, Zach? No, it's because the difference isn't 1. If you subtract these. If you subtract these, you get 4, okay? It has to be a 1 for it to be a slant asymptote, okay? All right, last one. Let me say it like this. What's the degree on top? Where's there a 1x? This was a 1. What is this? 0. How many x's do we have? 0. So you don't write this, but that's technically what it is. X to the 0 is 1. 1 times 6 is 6. We just don't write it. But just know, if you don't see a 0, you have no zeros. Nothing in math means 0. 0 is less than 2, so that is y equals 0. So A and D are the same type. Numerator was less than the denominator. Okay? All right. Homework time. It's on page 115. And I'm going to do number 1 with you. Okay. I wanted to do this one with you. It's just like just going back to polynomials again. And this is I want to go over the factoring of this one. Guys, remember the So it says to write an equivalent representation and sketch the graph. So we have to factor it, find the zeros, and then put it on the graph. So remember, the first step of all factoring is to factor out a GCF if there is one. And there's definitely x squared that they all have in common. But I want to remind you that anytime the first term is negative, you also factor out a negative. You never want your leading term to be negative when you factor. So we're going to take out a negative x squared from each of these. So we're going to take two x's away from it, and by having a negative, it changes the sign. If you're struggling at that step, just do the distributive property real quick in your head, and you'll see that you did it right or wrong. Okay, and as always, make sure you factored completely. Especially a problem like this, guys, you know there's going to be zeros you're going to have to put on the graph, so you have to have factors you can set equal to 0, okay? And we already had this one. This would be positive 3 and negative 2. Multiplies to get negative 6, adds to get 1. Let's find the x-intercepts, or the zeros. If I set each of these equal to 0 and solve, I get my zeros. I don't think anyone would struggle with negative 3 and 2, right? That's this guy and this guy. But don't forget, you can set negative x squared equal to 0. You get solutions from your x's, just not in real life. Think about that, okay? We had a problem yesterday that had a 2 out in front of something, okay? 2 is a factor, but it doesn't contain an x, so we don't get a 0 from it, okay? If you have an x attached to you, you have a 0 attached to you. Okay, so if I set negative x squared equal to 0 and solve it, I just get 0. Okay, but notice this. These two are singles, right? There's only one negative 3. There's only one 2. Those are going to cross the x-axis. Remember, odd number multiplicity crosses. But there are 2 zeros. That is a bounce, also known as a touch and turn. Because there's, how many negative 3s do we have? 1. How many 2s do we have? 1. There's only one of them. And that's odd. Odd crosses. So if you have 1 of the same number, or 3 of the same number, or 5 of the same number, you're cross at that number. 2, 4, 6, 8 of the same number, we bounce. One more thing we need is end behavior. All we care about is the leading term. Oops. Remember this, if your degree is even, you have same end behavior. You're either going to go up, up, or down, down. What's this one going to do? Down, down. Sorry, I kind of made a mess of the space. The only thing we don't have is the turnaround. You turn around where you want to turn around. It doesn't matter, okay? So I'm going to start down, and I'm going to cross through the negative 3, right? Turn around wherever you want and head back towards your next 0, which is at 0. And our 0, 0 is a bounce. So I touch and turn. And then turn around wherever you want. Hit your next 0 and cross. And we end down. So down, down, just like a parabola with a sad face, right? All righty. You have some time to work. Let's get some things done. Do you have it written down, Sam? What took so long? No. Then you hold everybody back because everyone's waiting for you so I can put this back up. You said I always do it at blah, blah, blah. It's also on the board behind me, or you can get it from Ryan. Yes, I yell at you every day, Sam. I don't know. Yeah. 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 Thank you for catching that. Nobody else did. Appreciate it. Now you're like, guys.
It's actually really hard to know who you're looking at.